We present STaR, Self-supervised tracking and reconstruction of rigid objects in motion with neural rendering. STaR is the first step towards the holy grail of spatial-temporal novel view synthesis. In other words, given a multi-view RGB video of a dynamic scene, we would like to render the scene from any point of view at any time. Here, we focus on scenes with a single dynamic object. Leveraging recent developments in neural rendering, STaR decomposes the scene into a static and a dynamic component, and simultaneously tracks the 60 poles of the dynamic content with respect to the static scene. Given this learned decomposition, we can synthesize the dynamic scene from a novel viewpoint at any point in time. We can also animate object motion completely unseen during training, with poses from a novel trajectory. STaR represents the underlying 3D scene as neural radiance fields, or NeRF. At the core of NeRF is a neural network approximated function that maps a 3D location plus a viewing direction to an RGB color and a scalar density. To obtain the color of a pixel, a neural renderer samples the points along a camera ray and integrates the radiance along the ray. Due to its continuous nature, NeRF can represent things with great detail. However, if there is dynamic content in the scene, the radiance at some locations changes with time, which breaks NeRF's assumption. Of course, we can train a NeRF for each time step, but this is time-consuming, and the model will not be able to render the scene at any time step not seen during training. We can also condition the network on time or time-dependent latent codes, but this only allows us to interpolate between non-time steps. In STaR, we opt for a different solution, which gives us full control over the scene. That is, optimize two separate NeRF volumes related by a rigid transformation. At each time step, we use the estimated object pose to transform the ray into the canonical frame of each volume. Compute the radiance along sample points independently for each volume, and then compose the radiance to obtain the pixel color for the original scene. In this way, we keep the networks parameterizing the two volumes time-independent, and handle time-dependent effects with the learned transformations. The factor representation enables our model to extrapolate beyond non-object poses. For example, we can predict what the scene will look like if the object continues moving, which cannot be achieved with the other solutions we discussed. Simultaneously optimizing the appearance and the pose can be challenging. We employed several optimization tricks to ensure the network does not get stuck in local minima. For more details, please refer to our paper. We first evaluate STaR on the task of synthesizing novel views of a dynamic scene at time steps unseen during training. STaR achieves superior reconstruction quality over baselines that uses time or time-dependent latent codes to model the dynamic content. Even on challenging real-world scenes with strong directional lighting and object symmetry, STaR is able to faithfully render the dynamic scene. Next, we use STaR to animate object trajectories that are completely different from the ones seen by the model during training. As we can see, STaR allows us to freely edit the dynamic content in the scene from a multi-view RGB video only. Finally, foreground and background removal is also simple with STaR's factored representation. Thank you. If you have more questions, please visit our website or come to our live session.